So good morning students, let's move ahead with our syllabus for the course. Just a quick recap of what we had done. I'm hoping that you have done the revision yourself before attending this class. So we have done the concept of random variables, what random variables are. So very quickly, in random variables, it is just a function of the experiment that we do and how it is related to the outcomes, and each of those outcomes are given numbers, right? Then we moved on to understanding what is a cumulative distribution function, CDF. So you can see on the screen that the CDF is going to give us the probability at specific points, and its final value is going to be 1. Therefore the CDF is a staircase function. The important property of the CDF is that we can find the probability at two different points, and you can subtract those 2 points, the CDF at those 2 points, to get the probability. Then from the CDF, we can get the probability density function, which is the derivative of the CDF. And we have seen using many numericals that the total area under this PDF is always going to be 1, right? Vice versa, you can also find the CDF from the PDF by integrating it. If you integrate the PDF from minus to plus infinity, that answer will be 1. But if you can also integrate it from some minus infinity to a value x to get the probability in that range. So based on these properties, we have solved many numericals. So I'm just showing you what we have done. And then we moved on to an important concept of PMF, that is probability mass function, which is similar to the concept of PDF. However, PMF is applicable when the random variables are discrete in nature. That is when they are when the values are available only at discrete points. That is, let's say 1, 2, 3. They will not be available at 1.5, 2.3, and so on. Right. So we defined what the PMF is, and that definition is there on your screen. So you can find the probability of x less than some value xi, where I is the discrete points starting at 1 going all the way till n. So n is the final value when we take the when we complete the experiment. Right? So the important property, like the CDF, like the PDF, is going to be that summation of all these probabilities is always going to be 1. So in the PDF, because it is used for continuous random variables, we use an integral with the limits, whereas for the PMF we use the summation because it is discrete in nature. Right? Then we saw how we could write the CDF of a discrete random variable. So for the CDF, we use the unit step function. The unit step function starts at the value of 0. It gets a value of 1 there, and it remains like that. That is, the value remains 1 till the final value, that is infinity or n. Right? So I've shown you on the graph on the left hand side how the unit step function looks like if it is discrete. At the bottom, I have shown you how the unit step function looks like if it is continuous in nature. Right? Then we also saw if you shift the unit step function by some xi to the right, what happens to the unit step function. Right? Then we saw mathematically how you can write this unit step function, and then how to write the CDF. Similarly, for the PDF, we can write it in the form of impulse function. The impulse function has a value of 1 only at 0. The rest of the times or rest of the values it will not occur. Right? And then we saw what happens to the impulse function if you shift it by some value xi. Right? We saw how we could write it mathematically, and then very important, we saw how we can solve numericals based on PMF. So it will always appear in the form of a table. I've explained you how we can find the CDF, PDF, how we can write the equations, and all of this is also available in the videos which I've shared on YouTube, and they are also available on Teams. So today let's begin with another important concept for random variables. This is very, very important because most of the analysis of communication engineering in terms of noise will be based on these concepts, right? So this concept is known as expectation, or in general expectations, because there are multiple such values, and as the name suggests, you are expecting something, right? There is a lot of expectation when it comes to noise, because noise is completely random in nature, and as I've explained you in the introductory lecture, it also makes the transmitted signal random, because we don't know whether noise will corrupt the transmitted signal. If it does corrupt, how much will it corrupt? What will be the value, and so on. So everything is random when it comes to noise. In terms of expectations, there are three values which we usually find out. There are many multiple values, but we'll concentrate on the three values because all other values can be found through these values. So the first expectation that we find is the mean or average, but we'll stick to the term mean. Okay. Second is a second order moment. It is not movement, it is moment. Okay, and I'll explain you what this is. And the third is variance. Okay. And you must know from mathematics in the first year, once you find the variance, you can find the square root of the variance and you'll get the standard deviation, right? So let's see what these expectations are and what this idea of moment is. Okay. So before we go into finding this these moments, let me give you a real-time example of what these what is meant by these expectations. Okay, so let's say this is the signal, this is the data that we have transmitted. Okay, so I'm keeping the y-axis as V, which denotes volts, or you can also denote it as amplitude, right? So this could have, let's say, a maximum amplitude of 10 volt and a minimum amplitude of negative 10 volt, and it is varying with respect to time, right? So this is your transmitted signal. Now let's say this signal, so let me redraw this signal. Now this signal gets corrupted by noise. So I'm just just drawing some random noise. Okay, so this is just a random noise. Okay, we don't know what is the shape of the signal. So you can see that this signal now, the transmitted signal, is now corrupted by noise. Right? So I want to know how much signal is corrupted. Now the initial voltage that we had transmitted for the signal is lying between 10 volt to negative 10 volt to plus 10 volt. Right? Now you can see in this diagram 2, okay, you can see in the diagram 2 that now the initial signal which we had transmitted is corrupted by noise, and you can see that the voltage has also increased or decreased, right? For example, if I concentrate at this point, you can see that the voltage value is much higher than the initial 10 volt, and here you can see that the lowest value is much below negative 10 volt, right? So when I receive this kind of a signal, I don't know whether the value is plus 10 volt or minus 10 volt. Now if I concentrate at this point where the sinusoid is crossing 0, you can see that the sinusoid is 0. The sinusoid is 0, or it is actually supposed to be 0, but the noise has gone to, let's say, some 5 volts, right? Or it has gone to, let's say, negative 2 volt here, right? So this noise is corrupting my signal and I don't know what is going to be the voltage, right? Therefore, to analyze this signal which is corrupted by the noise, we use the mean. Mean means it's going to average the entire signal, corrupted signal, and we'll get a value. So instead of just 5 here at the maximum value, instead of just 5 here at the maximum value, where the actual value is supposed to be 0, because of averaging, I may just get, let's say, 1 volt. Even though that is not a correct value, even though that is not the correct value of 0 volt, I'm still close to it, right? So mean value, when you find the average, right, you always get a closer value to the actual value, right? For example, a very common example is the marks, right? So someone has got let's say 90, someone else has got let's say 50. So there's a gap, but for the entire class we take an average and we say, okay, the average value is 60. There are some people more than 60, there are some people who got less than 60, but the average is 60, right? So we are close to the actual value, right? So that is the whole idea of mean. Okay, so this mean here, this mean that we calculate here, because it is the closest value and this is the first thing that we do to find whether the signal is whether the value is close to the actual value or not, it is known as the first moment. Okay, because it is the moment moment around the actual value. Moment around the actual value. It is the moment around the actual value, right? So please note, we are never going to get the actual value, because noise, we don't know how it's going to corrupt it, but we want to be close to the actual value, right? So let's see how we can calculate this mean. We'll go to second order moment and variance after we do the mean. Okay. So the mean, it is defined as an expectation operator, right? It is defined as an expectation operator, and we are going to stick to E of some value, and we'll fill this value very soon, right? And this operates on the random variable, defined as an expectation operator operating on a random variable, capital X, right? So how is this mean defined? So this mean is defined as, if the random variable is X, you have E of X, and this is defined as negative to positive infinity X fx of X dx. So X is the value of the random variable, and this multiplies with the PDF of the random variable. This multiplies with the PDF of the random variable. In statistics, you can also denote this E of X as mu X. This is another way to denote the mean, mu X or E of X. Okay, so this mu X and E of X will be used, interchangeably depending on the numerical, right? So that's how we define the mean of the random variable. Okay, so let me erase that PDF here. So this is the definition. This will be very useful for us in solving all the numericals. Okay, so all you have to do is take the PDF, multiply it with X or the random variable. If it is the random variable is Y, then you just have Y fy of Y, right? If you have Z, then it is just going to be fz of Z. So based on that, that's how we can define the mean of the random variable. Okay, so keep that equation in mind. We'll be solving a lot of numericals, and you'll know exactly how it is put to use. Okay. Okay. Now next, let's look at the second order moment. So second order moment. Keep in mind that the mean is also the first order moment or the first moment. Okay, but we're not going to use that aspect much in solving the problems. It will be more like the mean which is going to be used, the value of mean, and the mu X that we are going to use. Okay. Now the second order moment is if before the definition, it is how much have we deviated from the mean. Because the mean is the first order moment, how much you deviate from the mean is the second order moment. So let me explain you this, okay, with the help of another example. Let the y-axis be some value we don't know, okay, and let the signal look something like this. Okay, so this is more like that ECG signal that you see. Okay. Now in this signal we find the mean value, and let's say the mean value turns out to be this value here, the dotted line, right? This is the mean value. Okay, now you always want to be on the mean value, because that is the value that you have calculated. However, this noise will make us deviate from the mean, because it adds, it subtracts, it could multiply, it could divide, we do not know, right? And that is going to make us deviate from the mean itself. Therefore, this deviation from the mean, let's say the arrow which I am drawing, this deviation from the mean is known as the second order moment. Second order moment is known as the second order moment. So how much do we deviate from the mean will be the second order moment. Okay, so how do we define it now? We define it as E of x square. Okay, mean was E of x, second order moment is E of x square, and it is simply negative to plus infinity x square fx of x dx. So the first order moment was mean, which is x fx of dx. The second order moment is E of x square, which is x square fx of x dx. Okay. So this equation again is going to be helpful for us, but we'll see that mostly in the numericals we'll be using the equation for mean and that of variance rather than the second order moment, right? However, it is still it is always good to know what the second order moment is. Okay. Then lastly, the third parameter of interest for us in this course is the variance, and this variance is denoted as sigma, and if the random variable is x, then you have sigma x square, and you must know from the mathematics in the first year that you can find the square root of this variance. So we write it as square root variance, which will be square root of sigma x square, which will be sigma x, and that will give us the standard deviation. So you can know from this word standard deviation. So the question is what are we deviating from, right? So that answer is in the second order moment, that we are deviating from the mean, right? That is why it is known as the standard deviation, right? So in the first year when we were taught about standard deviation, we only knew that it is sigma x and some value, but we never probably questioned why it is called standard deviation. What are we deviating from, right? So the answer there is that we are deviating from the first order moment, that is the mean value, right? We always want to be near the mean value because that is closest to the actual value, right? So how do we define this variance, right? So variance is going to be denoted as variance in short. If the random variable is x, then you have var of x, and that will be E of x minus mu x the whole square, where x is the random variable and mu x is the mean. And you can also write this as, and we'll derive this a little later, you can also write this as E of x square minus mu x the whole square, and that will be nothing but sigma x square. Okay, so we are going to now derive this value, how E of x minus mu x the whole square is E of x square minus mu x the whole square, right? So let us prove that. So let me write this as 1. So prove that variance of x is E of x square minus mu x the whole square. So the proof is here. So let us first write the definition of the variance. So the variance of x is E of x minus mu x the whole square. Okay. Now I'm going to write this variance of x as sigma x square, and I'm going to open the bracket on the right hand side. That means I'm going to open x minus mu x the whole square. So you have E of, once you open the bracket, it is more like a minus b the whole square. So you'll have a square, which is x square, plus b square, which is mu x square, minus 2ab. So you'll have 2x mu x, right? Therefore, sigma x square. Now expectation is a linear operator. Therefore, I am going to have expectation of each value. So you'll have E of x square plus E of mu x square minus E of 2x mu x. Then you have sigma x square you have E of x square plus, now in the second term, if you see, let me mark this with a square bracket here, E of mu of x square. Now mu of x itself is an expectation. That means mu of x itself is an mean value. So there is no question of finding expectation of the expectation, right? You can't find the mean value of a mean value. Doesn't make sense, right? Therefore, this value, the second term here, there is no question of finding any expectation. So it's just going to be mu x square, right? Minus. Now in the third term here, you have a constant 2. So finding the mean of a constant doesn't make sense because we are only dealing with random values. So I'm going to take the 2 outside, right? Again, if you see the third term, you have a mu x in that term. So it is same as the second term where we are finding the expectation of an expectation. Doesn't make sense, right? So I'm going to take the mu x also outside, and then you have E of just x left. Right, so I hope you are able to understand what is happening in the second and third term. In the second term, you have E of mu x square, where mu x itself is a mean value. So there's no question of finding again the expectation. So you just have mu x square. In the third term, 2 is a constant. Mu x is again the expectation. So there's no question of finding expectation again. So I've taken 2 mu x outside the bracket, and then you have E of x, right? Therefore, sigma x square will now become E of x square plus mu x square minus 2 mu x. Now E of x is nothing but mu x again, right? So you will multiply this with mu x. So therefore this becomes E of x square plus mu x square minus 2 mu x square. Therefore, finally, sigma x square will be E of x square, and you can take these two together and you'll have negative mu x square. So this is the mathematical expression that we will be using most of the time to solve the numericals. So I hope this was clear, right? You can also what will be useful for us sometimes in the numericals will be writing this equation in other form. So the other form would be just bringing the terms on the left hand side and right hand side. So E of x square, that is the second moment, is nothing but sigma x square plus mu x square. So you can see what I had told you while defining the second moment. It is the deviation about the mean, right? So the term on the left hand side is the second order moment. The terms on the right hand side, you can see you have mu x square plus a value. That value is sigma x. So how much are you deviating about the mean value? That is what is your second order moment, right? Now what is the use of all of this? So let me give you a practical application of this. So in a practical application, E of x square is the total power. The sigma x square is AC power, and mu x square is DC power. That is a constant, right? Therefore, if you take these, the total power, that is E of x square, will be sigma x square, that is the AC power plus the DC, right? Now, in this equation, first up, if mu x is 0, that means if you do not have any DC, then signal is a pure AC signal, right? So what do you get? You get E of x square is sigma x square, which is nothing but AC power, right? This is what you would have studied in electronics. When there is no DC signal, all you get is just AC, fluctuating signal, right? If sigma x is 0, signal is pure DC signal. This is the kind of signal that we require for charging our laptops, mobile batteries. We need a pure DC signal, a constant signal, right? And in this case, E of x square will just be purely mu x square, and all you get is DC power, right? So this is what we can. This is what is a practical application of the mean and variance. But we are more interested in using these values of mean, variance, and various expectations to apply it for communication engineering. That is when the noise comes in, right? Okay. An extension of what we have done is the standard deviation, which can be derived from the variance itself, and the standard deviation sigma x is root of variance of x, and we use the mod value. It should not be a negative value, right? Because sigma x, the standard deviation, is always positive. Okay, you cannot deviate on a negative side from the mean value. You always deviate from a positive side, when it comes to standard deviation. So a few important concepts or properties which will be useful for us, and we'll encounter them during the numericals as well. First, if you have e of a function, e of g of x, then it is simply negative to plus infinity g of x fx of x dx, right? So whether it is a random variable x or a function, it doesn't matter. The equation for the expectation remains the same. E of any constant is the constant itself. So example is e of 5 will be 5, right? Third property, and we'll prove this property when we solve the numerical. So don't worry about how these have come. We'll actually prove them, right? Third is e of mu x, which we used to find the alternate definition of the variance, is just going to be mu x. Fourth, e of a x plus b, where a and b are constants and x is a random variable, will be a e of x plus b, because finding the expectation of a constant a does not make sense. We are here talking only about finding the expectation of a random variable, right? Very important for us to know, mu x, sigma x square, sigma x, all these values are constants. So you will never get expectation as 5 into x. You will never get variance as 6 into x. Not possible. It's a constant value. You'll get 5, 10, 15, and so on. Okay. So if you get any value multiplied by x, x square, y square, then you've gone wrong somewhere. Okay. So it's always going to be a constant value. Okay. So now, having done this, now let's look at some numericals, and we'll get more insight into finding the, in understanding the expectation values and the variance values. Okay. So let's look at the first numerical. The first numerical is the PDF of a random variable y, capital Y, is given as fy of y is 1.5, this is 1.5 into 1 minus y square, and this is for y between 0 and 1 and 0 otherwise. And the question is, determine one, mean. Second, mean of the square. Third, variance. So these are the three values which we need to find. Okay. So let's look at each part one by one. Okay. So in the first part, we need to find the mean value. And we know that the mean of any random variable, in this case, the random variable is y. So E of y is nothing but negative to positive infinity y f y of y dy, right? So it's simply just integrating and multiplying with y, the PDF is already given to us. Okay, so let me scroll a little so you can see the PDF. So I'm going to now write E of y as mu y because it's the mean value, and now I'm going to substitute the values inside that integral. You can see that the PDF lies between 0 and 1 because the value of y is only between 0 and 1. Only between those values the PDF exists. Therefore, the integral will have a limit of 0 to 1. You'll have y as it is, and between 0 and 1 the PDF is 1.5 into 1 minus y square, and the variable here for integral will be dy. So you can see what we have done. The definition of mean is y fy of y dy integral. We have just substituted the limit values and substituted the value of the PDF, right? So now from now on it just turns out to be solving the integral. That's all, right? So now in this case, mu y on the LHS will be, now let's start multiplying and then finding what will happen. So I'll take the 1.5 outside, it's a constant. You'll have integral 0 to 1, and you'll have y minus y cube dy. I've just multiplied this y with the 1 minus y square inside the bracket. Okay, so you'll have y minus y cube there. Okay. And then you'll have 1.5. Now let's integrate. So you have y dy, which will give you y square by 2, and then you have y raised to minus 3, which will be y raised to 4 divided by 4, and this limits will be from 0 to 1 here. So therefore mu y, now let's substitute the first limit here. So we'll have 1 by 2 minus 1 by 4 minus 0 plus 0, right? So you have 1.5 into 2 by 4 to be 1.5 let me see, I think I made a mistake. This should be 1 by 4. So 1.5 divided by 4. Therefore mu y, in form of decimal, this value will be 0.375, right? So as I told you before, the mean, variance, standard deviation, these will all be a constant value. So the mean value that we get here is 0.375. Okay. Now let's see what was the second value we needed to find. We wanted to find the mean of the square. Now what do you mean by mean of the square? Okay. So let me rewrite that here so it is clear to all of us. In the second part, we need to find mean of the square. So mean of the square means mean of the square of the random variable. So we need to find mean of the square. So let me first square the random variable. And how do you find the mean? You find the mean by just finding the expectation, right? So this mean of the square basically implies second moment. So all you have to do is just find E of y square. Okay. So how do you define E of y square? It is just an extension of E of y. This will be from negative to plus infinity and integral y square fy of y dy. Right. So let me rewrite this integral with the limits. So the limit for the random variable is from 0 to 1. You'll have y square, and let me insert the PDF, which is 1.5 into 1 minus y square dy. Therefore, E of y square. Now let's get the 1.5 outside the integral, and you'll have 0 to 1. And let's multiply the y square with 1 minus y square. It will have y square minus y raised to 4 dy, which will be 1.5 integral 0 to 1 y cube by 3 minus y raised to 5 by 5 dy. So you can see that once you write the equation, it just turns out to be doing an integration. That's all. So if you're good with the integration part, then nothing to worry about. So here you get 1.5, 1 by 3 minus 1 by 5 minus 0 plus 0. So you'll have 1.5 into 1 by 3 minus 1 by 5. And this is a 0. And therefore, E of y square will be, use the calculator, you get a 0.2. E of y square is 0.2. Right? You can see it's simple integration just after using the appropriate equation. Okay. And the third value which we need to find is the variance. So we need to find sigma x square, and we know that there are two equations for sigma x square, but we have already found the second moment and we have already found the mean also, right? So let me write the equation of the variance. Sigma x square is E of x minus mu x the whole square, and we have proved that this is nothing but E of x square minus mu x the whole square. Right? And from the first and the second values, we already have E of y square and mu y with us, right? So let me write this variance in the form of y, right? Because the random variable given to us is y, right? So I'll change this to sigma y square, which is E of y minus mu y, and this will be E of y square minus mu y the whole square. Therefore, sigma y square is E of y square, which you can see is 0.2, minus sigma mu y square, and mu y is 0.375, right? So you'll have 0.2 minus 0.375 the whole square. Okay. Somewhere where students make mistake is here. This value here is E of y square, and usually students just square E of y square again because they only look at y square. Okay, please understand, E of y square itself is 0.2, so no need to square it. Okay, E of y square is only 0.2, so no need to square that. Okay. So you have 0.2 minus 0.375 the whole square, and this value is, you get somewhere around 0.059375. So you can see that all the moments are just a constant value. Okay, and that's how it is supposed to be. If you get any moment which is in terms of the random variable, then we have gone wrong somewhere. Okay, so please keep that in mind. I hope this was clear. This is simple if we are able to understand the the equations. Of course, questions are not asked in this subject of what is the concept of mean and variance, moment, but it is always good to understand what they imply. Like mean because the noise is random, second moment because it is deviating around the mean value. That's why it is called as a variance. It's just varying about the mean. Standard deviation because it is deviating about the mean. So it's always good to know these concepts. They will help you visualize more, in the communication subjects. Because in communication subjects, everything has to be visualized. Because you start with signal, and the signal itself you cannot see, right? So everything has to be visualized. So you'll have to visualize how this noise is getting added, what mean are we finding, right? So this is something new for you compared to electronics, where you can actually see the resistor, capacitor. Of course you cannot see flow of electrons, but still you can see some device, and you can, then it helps you visualize. But in communication, everything is visualization. So here you'll have to, have the mathematics proper in your mind, so that you can understand what we are doing, what is it that we are trying to find. Okay. uh, let's look at another numerical. We have time for that. So the second numerical, it is given that it is given that E of x is 2 and E of x square is 6. The question is, find the standard deviation of x, and b, if y is 6x square plus 2x minus 13, find mu y. Find mu y. So let's take the first part that we need to find, and then we'll look at the second part, right? So we are given E of x, and we are given E of x square, and we need to find the standard deviation. This is a simple part. The standard deviation is sigma x. Before that, let's find the variance. Once we have the variance, we can find the square root, right? So sigma x square is E of x minus mu x the whole square. And we have proved that this can be written as E of x square minus mu x the whole square, right? Therefore, for this problem, sigma x square will be E of x square, which is given to us as 6, minus mu x the whole square. Mu x is 2, so you'll have 2 square. So you have 6 minus 4, which is 2. Therefore, the standard deviation sigma x is root of sigma x square. Therefore, that is going to be root 2, and root 2 is 1.414, right? So that was a simple part to solve. All the values were given to us, right? Now in the second part, we are given a different random variable y. However, that y is related to the given random variable x in the form 6x square plus 2x minus 13, and we need to find the mean of the new random variable, which is y, right? So this is a tricky part. Now let's see how we can solve that. Okay, so let me have it in the way you can see that part B. Okay. Okay, so we need to find the mean of y, and let me rewrite it quickly so we can scroll down. Y is 6x square plus 2x minus 13. Okay, now I can scroll down. Okay, so mean of the random variable y, right? And I'll denote this as mu y, which is E of y, right? Now instead of E of y, I'll write it as E of, and I will substitute y equal to the x value. So I'll have 6x square plus 2x minus 13. Now mu y on the LHS will become, now expectation here is a linear operator. Therefore, I'm going to write this as E of 6x square plus E of 2x minus E of 13, right? Therefore, mu y will become, now in the first term here, You have E of 6x square. 6 is a constant, so I'll get that out. You have 6 and you'll have E of x square plus, again in the second term you have E of 2x, so I'll get the 2 out and you'll have E of x, minus in the third term you have E of 13, where 13 is a constant and the expectation of a constant is a constant itself. So I'm just going to write it as 13, right? Therefore, mu of y will be 6. Now, E of x square is already given to us, and the value of E of x square, which is given to us in the question, is 6. Therefore, you'll have 6 into 6 plus 2. The value of E of x, that is the mean value, is already given to us in the question, which is 2. So you'll have 2 into 2 minus 13. Right? So this will be 36 plus 4 minus 13, and that turns out to be 27. So mu y is 27. So you can see that we were given a random variable x, and we were given a new random variable y, which could be which is related to the new random variable x, the old random variable x, and using the information from that random variable we could find the mean value of y, right? So there are many more questions based on expectation and variance which we can solve. So I've given you the idea of what mean is, what variance is, what is the second order moment, and we have looked at initial numericals of the based on expectation and variance. So in the next lecture we'll proceed with finding more with solving more numericals based on the expectation and variance. And very importantly, we also want to do this for discrete random variables, where instead of PDF we'll be using the PMF. So we want to see how we can do that. All of this is being done so that we can move towards specific PDFs, like the uniform PDF, Gaussian PDF, Poisson PDF. So there are specific PDFs for which you can find the mean and the variance values. So that is exactly what we need to do here.